Mojave Transportation Museum. We don't have a building, so the whole airport is a museum. It was a Marine Corps air station in World War II, was built in 1942. The airport was actually built in 1935. It was a dirt strip to haul gold for the gold mines. They hauled it up to Sacramento to be processed and refined. And then the Marines, as a matter of fact, General William J. Fox came here and chose Mojave as one of the Marine Corps air station where they would train pilots. And quite a few squadrons were formed here. Pappy Boyington actually flew out of here. So this building and the tower was here in 1942. It, of course, has been renovated, but many of the buildings on the airport were built in 42. There's still, I think, 2 or 3 hangars on the flight line that are vintage 42. And they are something else to tear down because they built things to last back then. And the swimming pool building is now the event center. And again, they thought about tearing that down. And I said, you ought to look at how it's constructed. And there's beautiful laminated beams that go clear across. And I mean, they're huge. And they decided, we better keep this. So the swimming pool was filled in. But the reason they had a pool was they would put the parachutes and everything on the pilots and then put them up on what they called a Dilbert dunker. And they would dump the pilots in upside down so that they, oh, Alexander's here, yay! So that they would know what to do if they had to do a water ditching in the airplanes. The ramp used to be full of F4U Corsairs. So anyway, it's the history here is pretty neat. The history of Mojave is neat. I'm wearing a shirt that we celebrated in 2017, the 140th anniversary of Mojave. Southern Pacific brought the railroad here in 1876. And then the wagon train that hauled the borax came here to load the borax onto the railhead that was here at Mojave. There's just so much neat transportation history. So anyway, we just felt a museum was important. But I'm going to introduce you to our fabulous speakers, and I hope you all had a chance to see that airplane sitting out on the ramp. I'm so excited. Alex Kroll is a former United States Air Force test pilot. He holds a BS and MS in aerospace engineering, an MBA, and an MS in flight test engineering. Now, he looks awful young to me, but then I've been on the planet a while. He's a distinguished graduate of the U.S. Air Force Test Pilot School here at Edwards. Has 2,500 hours of flight time and over 50 different aircraft. He's currently the chief test pilot at Universal Hydrogen. He holds an air transport pilot certificate and is type rated in the Boeing 737, the de Havilland Dash 8, like the one out front, and F-16s. And here with Alex today is Loris Gleiner. He's the director of powertrain engineering. I didn't know whether to call that a motor or an engine, because if it's electric, it's a motor. If it's runs on fuel or gas, it's an engine anyway, so they call it a powertrain. Okay. But he is in charge, the director of the flight test here at Universal Hydrogen, and leads the development of the 2 megawatt hydrogen electric powertrain for regional aircraft. He joined Universal Hydrogen in 2020 and is the company's second employee. Prior to working for Universal Hydrogen, he worked at Airbus up next in Toulouse, France, and he's actually from France. But he researched autonomous taxi, takeoff, and landing technologies for large commercial aircraft as part of the Airbus ATTOL A350 demonstrator. But he was a team member of the Perlin Project. Now, I don't know if any of you know what the Perlin Project is, but our friend Jim Payne is a pilot on that. And that's a project to fly in the stratosphere, take a glider up and conduct high altitude scientific research. But there's a vortex over the South Pole, and they can get in that and really go high. This last year it just wasn't working and they didn't go very high. But a few years ago, they went up to 76,000 feet in a glider. I mean, that's pretty awesome. And Loris was privileged to be part of that. I think that's really cool. And and that was down, they were at Patagonia, Argentina. But I think it was 2018 when they did that. So, and that surpassed the U-2 spy plane and set a world record, altitude record for subsonic flight. Loris has a master's degree in aerospace engineering from Imperial College in London, and he is a licensed pilot. Please welcome Alex Kroll and Loris Gleim.
Yeah, thanks everyone for coming to listen. Thanks, Kathy, for the introductions. I know we're kind of new kids on the block at Mojave. We'll get into that as we go through the brief. So this is the exact brief that we recently gave at the Society of Experimental Test Pilots. Some of you may have seen it already. So I guess you know the answers to a lot of the likely questions that we're going to get. But in that vein, it's more flight test related. We're going to go through about 25 minutes of this and then open it up to questions. So we ask that there's no recording unless we've kind of previously chatted about it. And then we'll just hold questions for the end. All good? Cool. Yeah, I'm Alex. This is Loris, and we're going to talk about the first flight of the world's largest hydrogen fuel cell powered aircraft. Flight. Standard kind of military format. This is what we're going to go through. This is what we're going to talk about. We're going to talk about it, and then we'll tell you what we talked about.
Do you want me to turn these lights out so it makes it easier to see, or?
That's kind of up to the audience. If you guys are all fine, then
Yeah, it's okay.
it's good.
Okay.
All right, we're good.
Cool.
All right,
Cool.
press. Yeah, so on March 2nd, 2023, we took this beast to the air. We were up in Moses Lake, Washington, Grant County International. So we set the flight record for the world's largest hydrogen fuel cell powered aircraft. It's the first transport category aircraft to fly on hydrogen fuel cell powered. Flew for about 15 minutes, consumed 16 kilograms of certified green hydrogen via our 1 megawatt experimental powertrain. So that was really the kickoff for these development efforts that we'll pursue over the next couple years. And our eventual goal is a STC on an ATR-72 for basically both motors powered by hydrogen fuel cell to produce a green, clean, fuel efficient, and financially viable regional transport aircraft. Slide. So what we started with was a perfectly good Dash 8, and we tore it apart. Dash 8 300. Our other pilot had actually flown it on the line at Piedmont many years before. It's originally powered by two Pratt & Whitney 123s, so it's produced about 2,200 horsepower apiece with a 43,000 pound max gross takeoff weight. So the reason we chose this aircraft, it was available and it was cheap, which is a good thing, but it's extremely docile single engine flying qualities. So giant dual segmented rudder, maximum deflection of 18 degrees, very low min speed for inertial control in the air. When you lose an engine, especially when you're testing power plants, it's probably a good quality to have in an aircraft. You want to make sure that it can fly effectively and safely on a single engine, the one that you're not modifying and experimenting with. It's very isolated and redundant on both sides, so you can basically cut the aircraft in half, and each half will fly perfectly fine without the other. So a lot of good single engine redundancy there. And then takeoff and landing performance was also very favorable. So these regularly operate out of runways of 3,000 feet or less.
Wow.
So knowing that we were going to, take a 2,200 horsepower motor, replace it with a 1,000 on the left-hand side or the right-hand side, we wanted to make sure that we were starting with an airplane that that we weren't concerned about performance or flying qualities issues. So bottom line is this was a stable, well-known, and reliable testbed for ride-along propulsion testing. And we'll kind of say that a lot throughout the brief. Our objective was to replace the right side motor and touch as little of the baseline aircraft as possible to isolate that experimental powertrain to the maximum extent possible. Play.
All right, so now we'll talk a little about the powertrain. So how it works, right, is we start with hydrogen molecules and then we generate mechanical torque for the propeller. So how does that work? Right, is if you've ever taken a AAA battery, put it in water, and then on one side you've got oxygen coming out and on the other side hydrogen coming out. That's basically how it works, but in reverse. So this is a schematic of the different systems that we have in the powertrain. The most two important ones, right, being an electric engine, so that takes the electrons generated by the fuel cell to generate the torque for the propeller, and then the fuel cell system, which takes the hydrogen, reacts it with oxygen to generate the electrons. We also have some balance of plant systems, which are there to ensure that we can run the system efficiently. So we have to compress the air before sending it to the fuel cell. We also have to condition the hydrogen, so depending whether it's gaseous or liquid hydrogen, we have to heat it up or cool it down before using it. And then we also have a thermal management system. Those are the two big radiators you might have been able to see on the airplane outside, which are used to cool the fuel cells, because as they generate the electricity, they heat up, and so we need to control their temperature. I think one thing that we want to point out is, so hydrogen propulsion is nothing new. It's been in cars for many, many years, and especially in California, the Toyota Mirai, right, is on the road every day, and you probably drive past them and you don't even realize it. The new thing that we're doing is our architecture is slightly different. In the electric propulsion that's currently being used in automotive or other aerospace project is really it's a hybrid system which relies on a very heavy buffer battery. So the buffer battery provides the power to the electric engine, and then the fuel cell really acts as a range extender, kind of recharging that battery. At Universal Hydrogen, we believe that this is not the way to go for aviation because it's super heavy, number one. Two, certifying high voltage battery is really complex. And then number three, from an economic standpoint, batteries are expensive to have as well because you have to replace them every 1,000 cycles or so. So we've taken a different approach where we have fuel cells powering directly the electric motor. So it's more challenging from a control standpoint because dealing with transients and ramping up and ramping down the fuel cell is quite tricky. And so that's why we developed the whole software in-house, and that's really the purpose of this flight demonstrator is we wanted to show that this can be done and we can reach the performance that we want. And so far it's been pretty successful. Slide. So we'll focus on two of the systems, the fuel cell system and the electric engine. So fuel cell system, we have what we call 6 fuel cell stacks in the airplane, and each stack is basically a cassette with many fuel cell plates, which react the hydrogen and the oxygen to generate the electricity. We've got 6 of them arranged in a 3S2P configuration, so we've got 3 parallel branches of 2 stacks in series. Why do we put the stacks in series? We connect them in series just to bring up our bus voltage to about 650 to 850 volts, which is our operating voltage for the electric motor. And so that gives us about 1 megawatt of gross power, about 1,200 horsepower. Slide. Oh, the one thing, the big takeaway bumper sticker at the end is that the only byproduct of that reaction of hydrogen and oxygen is water. So when we fly around and when we did the flight a few weeks back in Mojave, you can see the water vapor coming out. It does not generate contrail, but you can see the water vapor, and that's the only emission. So there's no carbon emission, no NOx emission. It's really clean reaction in the process. Slide. So then the other really important system is our electric, what we call the electric engine for the FAA terminology. So that electric engine is really an electric motor as well as inverters / motor controllers to control the electric motor. So The inverters take DC power from the fuel cells, convert it to AC power to run the electric motor. The motor that we're using is from a company called MagniX, which is based in Seattle, in Washington, and it's about 1,000 horsepower. So that's about half of the Pratt & Whitney we replaced, right? Ultimately, when we put this product on the market, it will generate the full 2,200 horsepower, 2 megawatt shaft that we need. But we as a company wanted to get to flight as soon as possible because that's where a lot of the engineering learnings happen. You can do PowerPoints all day, but really you're going to discover the real problems when you put those systems in the air. So we took the approach of let's find the biggest motor that's available today and rely on off-the-shelf components as much as possible. Let's fly in as soon as possible, learn it. This is our demonstration phase. We'll mature the system, and then once we've got the good system maturity, then we'll move to the product phase and certify it, which is going to be our next phase as a company. The propeller that we use is also slightly different, as I'm sure you've seen. It's much smaller, and the reason why we're using a much smaller propeller is well, we've only got about half the power, and the other reason is that electric motor spins at up to 2,300 RPM, which is about twice of what the Pratt & Whitney spins at, which is 1,200 RPM max. So if you're spinning faster, your blades have to be shorter, otherwise you're going to get supersonic at the tips. So we're using a propeller from Hartzell. It's actually the blades is from the TBM 900 series aircraft. Slide. And then our hydrogen storage. So right now we're relying on gaseous hydrogen storage. So we store hydrogen at the back of the fuselage at a pressure of 350 bars, about 5K psi. And we store those in modules which are of automotive provenance. So they've been certified to automotive standards. And so they've been through very, very rigorous testing, including bonfires, shooting at them with a 50 cal, and they've passed all these tests, structural tests as well, burst tests. So we've got very high confidence in the safety of the system. Ultimately, our goal as the company is to fly with liquid hydrogen, and that's an upgrade we're going to do on the airplane next year. So we're going to replace these modules and put liquid hydrogen instead. Why do we want to go to liquid hydrogen? A few reasons for that. First thing is liquid hydrogen is much lighter, and it's the same weight, but it's the tanks are lighter, and the volume is much smaller, meaning that we can, for the same amount of volume in the fuselage, we can quadruple our range, essentially, compared to the 350 bar system. And then the other thing is we believe that certifying liquid hydrogen is also going to be easier because we're not working with extremely high pressures. Certifying very high pressure vessels is complex. Liquid hydrogen is, we're going up to 10 bars or about 150 psi, so that's much more common for aerospace and much easier to certify. All right.
Cool. Yeah. So talking about some of the human-machine interface, new powertrains require new interactions with the pilot. There's no real standard accepted standard for electric or fuel cell aircraft, so we were kind of left to our own devices to create our own. Our philosophy here was simplicity, and then try to parallel the baseline aircraft as much as possible. So our ICAS, our engine indication control alerting and caution alerting system, is on the right-hand side. As you notice, there's probably a lot of familiar gauges there: torque, prop speed, temperature, high voltage bus, and that's our primary indicator of the health of the system. So we're setting torque, we're setting prop, but really how happy the fuel cell is your high voltage bus, which may be equivalent to like an NG or like an ITT type indication in a conventional turbine motor. For the control, it's a pretty simple panel. So really it's 3 switches to turn it on, 3 switches to turn it off. The boot up sequence is completely autonomous. And then our big our test, our orange wire kind of control button is that e-stop. So being that this is an experimental powertrain, we wanted to design it so that the aircraft flies perfectly fine without the fuel cell motor. And that anything that goes wrong, that we can reserve the option to just shut it all down, land safely, and then analyze the problem on the ground without threat to the aircraft or aircrew. So what that button does, it's accessible to both pilots. It's in the center. It's easy just to we get a caution or a warning, hit the button, it removes power from all the relays, so it shuts down the motor, shuts down the fuel cell, and then closes off the hydrogen tanks. So it stores H2 in the tanks, and then actually keeps that EMS running, so we can still monitor the status of the system. But being that the tanks themselves are certified for road use, we've assessed that that is the safest place for hydrogen. I know people hear hydrogen and they get ideas, but the really truly the safest place for it is in those tanks at high pressure. So we're moving all energy from those relays, basically shuts down that flow of hydrogen to the fuel cell. Slide. So our test philosophy was, I've said it before, I'll say it again multiple times throughout this, utilize a stable, well-known platform as a test bed. Powertrains are right along. So out at on 3.0, we could take off single engine in the Dash 8. It wouldn't be great, but you could do it, which is kind of really fed our decision making as far as buying that aircraft. Isolate as much of the baseline aircraft from the system under test as possible, and then use the hardware in the loop lab. So we'll see a couple slides later. We have basically a 99% common software and hardware common ground test bed that we use to test software, test their architecture, etc. And we've been using that heavily. And then minimize the pathway to first flight, even if it means reducing capability. So, simple, fast. This is, like we said before, this is a prototype. It's not our full, market product. It doesn't have that same capability, but it's able to get in the air. We can learn quickly, and then kind of optimize from there. Slide. So we've identified a couple major risks to flight tests. Again, this is a flight test oriented briefing. One being hydrogen, just powertrain maturity overall, and then modified aircraft performance. So we've mitigated those risks through design and the operations and planning process, and we'll talk about that more over the next couple slides.
All right, so yeah, hydrogen. Hydrogen is new to aviation, so it has a different set of challenges than jet fuel. But I think the bumper sticker is it's a different set of challenges, but you can make it as safe, if not safer than jet fuel, and we'll go into that a little later. So what are the risks with hydrogen? Well, the first thing is hydrogen is the smallest molecule on the periodic table. So it's super small. It wants to leak, especially when you have it at high pressure. It just wants to leak, and it permeates a lot of materials out there. The second risk with hydrogen is that it's got a very wide flammability range when compared to jet fuel. So hydrogen is flammable in concentrations 4 to 75% in volume in air, and then it's explosive in concentrations in 17% and 59%. So in all cases, you want to be outside the flammable region, and you definitely don't want to be in the explosive region. And then the third major risk with hydrogen is that it has a low ignition energy. So wide range of flammability, and then especially when you're at the 17%, as you see on the graph on the right, low ignition energy. So it wants to ignite. Next. So how we manage this for our first flight? The first thing is we use certified parts and off-the-shelf parts. So it's something new for aviation. Let's not try things that are too new. So let's rely on components that have been used and certified for years in automotive and that have been proven to work right. So that's what I think was one of our biggest mitigations. The other thing is hydrogen is very easy to sense. So you can have extremely accurate hydrogen concentration sensors. And the other thing is hydrogen being so light, it doesn't pool. So if you have a hydrogen leak, what does it want to do? It's going to go straight up. So it's also very easy to place those hydrogen sensors in places where the hydrogen is most likely to accumulate. Meaning that, hey, hydrogen wants to leak, but the good news is if it leaks, it's very easy to detect that leak. And so what we've done is we've placed hydrogen sensors pretty much everywhere in the airplane. Storage modules, cabin, powertrain, and we've got 2 completely independent and redundant systems to detect those leaks. So if there's a leak, we have very high confidence that we're going to detect it in the airplane. And then the last thing that we do is wide flammability range, which we want to avoid. So how do we do that? Well, we detect the leak and then we ventilate. So we have a special ventilation system. We reuse the pack, air conditioning pack of the aircraft, and we can continuously ventilate the hydrogen storage modules and the powertrain. And we have 2 operating modes. We have a low flow mode, which is our normal operation, because if you ventilate a lot, it means that, if you have a small leak, you're not going to detect it because you're going to dilute the hydrogen concentration very fast. So normal operation, low flow, meaning that if there's a leak, we're going to detect it straight away. And then if we do detect the leak, then we go to high flow, so we're going to dilute the hydrogen and ensure that we always remain below our 4% concentration level, meaning that we can't, get to the flammability reaching. Slide.
Cool, yeah, so another risk that we identified during the design process is just single engine operation. We wanted to make sure that we were giving it its due, even though we knew that the aircraft performance was adequate based on where we're operating and what we're putting on the aircraft and the envelope that we're flying in. So we wanted to ensure that the aircraft is capable of level flight single engine, but not only using the hydrogen powertrain. So we've admitted already that the right side of the aircraft is about half the power of the left side. So we needed to, that was kind of one of our entering arguments from a design and operational risk management process. Relying on the Pratt & Whitney for accessories and support systems, so moving that philosophy forward, isolating the right side, the experimental side from the baseline aircraft. That means that now you've lost that redundancy, hydraulic, bleed air, electrical systems, etc. The H2 powertrain requires aircraft DC power, so it'll run for a set number of minutes, if there was a complete electrical failure, but it'll be draining those batteries. So that's just another consideration. And then, of course, in tests, there's, the known knowns, the known unknowns, and then the unknown unknowns. So unknown impact of the interference from the system under test is always kind of lingering in the background that we wanted to control for. Slide. Yeah, it's not super repetitive, but definitely isolate, our design risk mitigation was isolate that experimental powertrain as much as possible. We want to deactivate an unnecessary system. So any interior, exterior lighting or electrical systems have all been deactivated. Our DI system, our right side fuel system, it's all taken out because that does two things. That reduces demand on the accessories and the turboprop, the remaining turboprop, but then also reduces potential ignition sources or just other things that can go wrong with integrating this experimental powertrain. We integrated a standalone backup power for some flight critical systems, so we do have some additional DC batteries that power some of the baseline standby systems, but independent of that operating turboprop. And then more from an operational perspective, we did a thorough emergency procedures review, development and rehearsal based on the aircraft as it is, not how we want it to be or how it was before we modified it. So integrating a lot of that system safety type stuff was pretty critical. Slide.
So we also did a ground test bed, which we ran for about a year before doing the first flight. So the picture you see on the screen here is our Iron Bird, and it doesn't look like it's the same system as on the airplane because it's everything's kind of far apart so that we can easily work on it. But from a functional standpoint, it's 99% representative, and similarly for the software. And so we've run this about 12 months before we did first flight and got close to hundreds of hours of testing on there. So we really ran it for its paces, tested willingly and unwillingly failure scenarios, right? Corner cases. We went to more power, less power. What happens if you run out of hydrogen? So we could really understand and know the system before we tried to put it on the airplane.
Yeah, so in build up to first flight, we matured the vehicle and our control processes, our comms, and crew resource management via a ground testing campaign. So low speed taxi is really just demonstrating the integration of the new powertrain on the vehicle under motion. And we could get a little bit of handling qualities analysis at low speed, just based on that difference of thrust. Our high-speed taxi testing is kind of really where the rubber met the road as far as on-aircraft performance testing. So we were able to validate some of our thrust and drag models, get a better idea of how the aircraft was going to fly once we got airborne. And then we were also able to develop some special procedures to deal with that asymmetry of thrust on takeoff. What was really important from this that I think that kind of went a long way is we set up the entire first flight test command and control structure. So everyone that was going to participate in first flight was part of all the ground tests. We had all the radios out, we had all the comms, we had the exact same cards. everything we were trying to build up, make it exactly the same as what we were going to see on that test day. So there's fewer surprises, but then there's also kind of more situational awareness and more kind of brain bites to deal with anything that could come up on test day. So kind of get that rote repetition so that when something unknown happens, you can deal with it. And then we also did a number of static rehearsals, so basically the same profile over time, but on the ground. So everything was kind of time representative. We didn't move, but we moved the power the same to try to, again, build that muscle memory. So there were a few operational risk management tools that we used to manage the hazards that we identified previously in the design process. So hydrogen, from an operational perspective, kind of our mantra is detect, isolate, ventilate. Laura's talked about that a little bit. We need to make sure that we can detect it. We do have H2 detectors. We get cautions and warnings at certain percentage levels, and those are redundant and independent. Isolate, so keep as much of that hydrogen in the tanks as possible. Hit the E-stop, shuts everything down, and preserves that hydrogen. And then ventilate. So going to the high flow ventilation mode dilutes the concentrations, and we've tested that on the ground extensively. So this was, anytime we get an amber or a red light, that's exactly what we're doing in the aircraft or on the ground. Sorry, in the air or on the ground. Operationally addressing another one of our hazards, single engine ops. So critical phases of flight, we want to make sure that takeoff and landing distance was not a factor. The runway we used was 13,500 feet long and 300 feet wide, so gives you plenty of time to make decisions. We knew that our takeoff distance was going to be extended. We analyzed that, about double what the baseline aircraft was going to be, and actually on first flight we validated that, and it came out pretty close. So there's no V1. If we've not rotated, your abort procedure is really simple. You just pull everything to idle, shut down the powertrain, and you don't have to worry about kind of takeoff or landing performance there. We developed a specific takeoff procedure also to minimize asymmetry. So given that you're at about half on the right side, half the thrust on the right side is the left side, we definitely wanted to make sure that we're not inducing too much of a moment once we push power up on the ground prior to that rudder coming alive at 40 knots. We created discrete abort and continuation criteria. So every step of the way, we wanted to make sure that not just is something going wrong and we're stopping, or is this actually going right? Like, so are we performing according to models? This is validate the assumptions that we've made kind of in our planning process. That gives us plenty of outs. So being able to put the aircraft back on the runway in case of a lack of performance, that's an out. Making a turn out to align with a more optimal runway is another out, that we want to make sure that every step of the way that we're making decisions based on the expected performance and the actual performance, and not kind of leading ourselves into those cognitive biases. That kind of ties in with number 4, so establish gates to validate failure models, and then we developed emergency procedures for kind of each one of those phases of flight, and we validated all that in the simulator, which is super nice, and we're going to talk about that probably next slide. So we designed a flight profile to maximize our ability to get the aircraft safely on the ground. There's an overhead of Grant County International and Moses Lake. There's a lot of crossing runways, which makes this job really easy, because you've got plenty of landing surface. But we wanted to approach this with a single engine mentality. We're not taking off with a failed powertrain, but we know that either one of those could really fail at any time, and we've already reduced the reliability of the aircraft by removing the certified motor. So we built that profile to maximize our landing opportunities, and we wanted to make sure that at all points we're within gliding distance of our airfield. We also wanted to minimize configuration changes, so we left the gear flaps down. We weren't performance constrained, but those were slightly disturbed systems since we were messing with the hydraulic systems on the right-hand side. We just wanted to keep things simple. Source flight, it's just as much for PR as it is for data, and we didn't want to do anything, make any actions that could further complicate our profile or our comms. We also minimized the need for power changes. Things often break when you change them, so we really wanted to keep that set and keep things simple. And I thought what was maybe not novel, but it was really effective for us is we rented the Cessna 172 and we flew the profile. We had the cards, we made all the same radio calls, we had the same command and control structure, include the same geographic references to familiarize our pilots and aircrew with the timing and the navigation, so that if something were to go wrong, or that they could really just focus on flying the aircraft. It's the most important thing. Slide. Cool. Getting to flight simulation, we did a lot of simulator time, and we did some kind of extreme stuff that we felt was very unlikely, but we wanted to kind of see everything and make sure that the aircraft was going to respond the way that we expected it to. So, bottom line here is, see as much as possible before flight. We thought this was probably our best money spent. We were able to integrate some of our thrust and drag models from analysis into the simulator. And then really, I think the sensitivity analysis was also really important. So like, what if our math is really wrong? What if it weighs, we know how much it weighs, but what if the drag is double what we calculated? What if the thrust is half? What if, and so we went through all those what ifs to make sure that the aircraft is still controllable. At the end of the day, we want to make sure that this airplane, once we take off, we have an option to land it. Slide. Cool, so our flight test objectives. We want to demonstrate, for first flight, demonstrate the hydrogen powertrain system integration, collect some basic aircraft performance data, kind of a limited observation of the modified aircraft flying qualities. So does it still fly like a Dash 8 overall? Is it better or worse than a single engine Dash 8? And just kind of record that for future use. And then get some cool pictures. So we'll have a video kind of towards the end. But yeah, it was a really picturesque flight. It was a good flight day. But at the end of the day, the objective of flight test is take off and then land the aircraft safely.
Yeah.
So do as little as you can to meet your objectives. No need to overcomplicate. Just for fun. So I think you may have to click the mouse. It should start playing automatically. Nope. Maybe go back in spacebar. Serious? All right, I'll pull the video up later. Sorry.
No, we'll wait.
So some of the technical lessons learned from that first flight is really the system behaved like we thought it would behave. So both the voltage, which is really the primary health indication of the system, was within the bounds that we had set for ourselves, and the power behavior was also expected. I think the other big thing is we validated our buffer-free battery architecture, and that's really the novel piece that we were bringing to the program, and we showed that we could power an electric motor directly with fuel cells with a buffer battery, and we strongly believe that this is the way to go for aviation, and this is what is going to make it possible to address these regional aircraft. We also had no thermal issues, so that's probably not a surprise given that we did the first flight on March 2nd and it was quite cold outside. But designing the radiators is probably the most technically challenging part of designing the powertrain. And so we gathered a lot of good data on that first flight that allowed us to validate our models and validate our CFD analysis, and those were kind of in line, so that was positive outcome of the first flight. And then the fourth one is it's quiet. So we don't remove the noise of the propeller. You still have that, but we remove the noise of the combustor turbine, compressor stages. And so really you can't, when you're in the airplane, you can't really hear the external powertrain because it's completely drowned out by the Pratt & Whitney noise.
It's really quiet on takeoff.
Yeah, so some operational lessons learned. Rehearsals and simulators are worth every dollar. We thought that was, it adds time and it adds money, but being able to kind of see every scenario on the ground in a safe place before taking it to the air is super valuable. It builds confidence in the crew. It builds their working relationships. It just makes flight tests go a lot smoother. Limit complexity, minimize the changes. So if you don't have to move something or change something, don't. Build time into the schedule to dig deeper. So I know a lot of smaller companies, runway might be limited from a financial standpoint or a schedule standpoint, but building in like a couple blocks of a couple days here, a few days here, just in case that you get an unexpected test result and that you can investigate further or determine if that even needs to be fixed, determine the impact to your flight test program without sliding the entire schedule. We had to do that a couple times, and it ended up working really well because we had a couple days to investigate further, and we're less schedule driven in that case. know what normal looks like. So our other pilot is like a 10,000 hour Dash 8 pilot. He's done everything that you can do in a Dash 8. So being able to have that experience, with a flight test aircrew that may not have as much operational experience in that same aircraft that you're testing, he knows what the system is supposed to look like. He can identify if things are way off, and that was just really helpful to have on our test program. And however you want to say it, kind of look through each phase of flight. What validates your model? What can go wrong here? And at what point is, there's kind of a spectrum of failure, right? So it may not be on or off. There may be somewhere in between where you might not be performing as predicted, but still adequate to continue test. So really thinking through all of that on the ground, validating in the simulator, and then again seeing it on the ground test was, I think, a really important aspect of our safety and risk management procedure. So actually, back one. We're not on fire on the right side. That's the water vapor we talked about earlier. So you can see that. If we run it on the ground at high power, there's like a huge water spot on the ground. It's kind of neat. But at the end of the day, I wanted to say, like, flight test best practices still apply. It's a new powertrain, new architecture, but propulsion testing, risk management, it's all still really the same. Fine. Cool, so where we go from here? Our phase 1 testing is complete. We've accomplished 10 flights. We ferried it down from Washington to Mojave back in June. That was an 800 nautical mile ferry flight. We did an hour runtime at 10,000 feet MSL on the powertrain, so that's a record for a hydrogen fuel cell powertrain period. Phase 2, we're starting in a couple weeks. Actually, it's basically a tech maturation and tech maturation campaign. So we're going to collect a lot of performance data, make incremental changes to optimize it, so we can build out that architecture before we, kind of build the market product, run it for SCOR for the STC certification. That's going to include envelope expansion up to 25,000 feet, integrating those liquid H2 storage modules, which we talked about earlier, and then that should conclude at the end of next year. But company, the objective is to make money. We want to sell these. So starting next year, well, we've already started development, but starting next year, we'll start constructing that Iron Bird of our market product. So a 2,000 horsepower hydrogen fuel cell,
Wow.
STC capable powertrain. So hopefully in the next 2026, we've got an aircraft that we can, we've got a product that we can sell to airlines, and we can see these turning on the line. Cool. Well, yeah, thank you.
Airlines, I saw the names on the sides of the airplane. And Southwest was there at your,
Yeah, we've got about 250 pre-orders for
Wow.
conversion kits.
250. That's awesome.
I'll start on the left. Yep.
Yeah, so I have two questions. The first one is, so from the original aircraft to the new version, what's the weight difference now?
So the aircraft, as is today with the modified system, is 4,700 pounds.
Okay.
The weight of the powertrain, I can't publicly disclose. It's heavier. It's heavier than the Pratt & Whitney that we're replacing. And even when we go to product on the ATR 72 and have the same power level, the new powertrain is still going to be heavier than the turboprop that we're replacing. But we're still making an airplane which can. So the ATR 72, right? Today is a 72-seat aircraft, and what we're doing is we're removing 3 rows of seats to store the liquid hydrogen at the back of the airplane. So 3 rows of seats, we're essentially removing 18 passengers. So we're a 56-seat aircraft instead of 72. And with with the heavier weight of the powertrain and the liquid hydrogen storage on board, we can still fit 56 passengers and respect our max takeoff weight on the aircraft. So the only capability that we degrade on the airplane is payload, because we go from 72 to 56, and range.
Yeah.
Today the airplane can probably do 2,000 nautical miles or slightly less. Our target with the hydrogen version is to do about 500 nautical miles. But that 500 nautical miles allows you to target 95% plus of the missions that these aircraft are covering today. So when our commercial team is going to airlines and presenting the specs of the aircraft, range is not an issue for these airlines. Now, one question that may come up, right, is, well, you're going from 72 passengers to 56. How does that impact the economics of the airplane? Are the tickets going to be a lot more expensive? Well, actually, our target in 2026, when the airplane enters into service, is that the price per passenger, so the metric that these airlines use is CASM, cost per available seat mile, should be the same as the incumbent turboprop version. Why is that? Even though hydrogen is still more expensive than jet fuel at that point, the hydrogen powertrain is about twice the efficiency of the turboprop. So you need 2 times less hydrogen or 2 times less energy. So that's a significant cost saving on your operating cost. The other thing is, fuel cells, electric motors, they operate at low temperatures. We're talking 100 C max, and they have relatively fewer moving parts compared to the turboprop, and they spin at a much lower speed. So maintenance costs are also lower, meaning that we can offer the same economics. And then when you look over time, where the price of hydrogen, green hydrogen, keeps going down, then economics get better. So really, it's a no-brainer for the airlines because they get an airplane which is completely carbon-free and costs less to operate. So that's the value proposition for them.
I got the video real quick. I'll give you a break. It's kind of neat. Standard promotional video. Yeah, this is our first flight chase video from Moses Lake.
Yeah, you can kind of see the water coming out of the powertrain. That's the only byproduct from the
Yeah, that was just the takeoff. For whatever reason, the other one's not working great. Let me. Yep. Yeah. I'll do this one. I don't know why this is- Sorry, I'm not as prepared as I should be.
You're great.
I'll pause it.
No, that's fine.
Let me let it pop.